Alright, so in this video I'm gonna be explaining another important article, graph units. Units is a very important architecture for image segmentation, but they also generalize it for graph as well. So we have a graph unit, the same kind of downsampling, upsampling, then reconstruction error. So everything is the same now, but it is now the graphs. The physical object is not image, it's a graph that is getting downsampled and upsampled. So this paper in 2019, so unit was in 2015. There was no equation in that, nothing. Very simple historical paper in 2015. But in 2019, we have these graph units. So we consider problem of representation learning for graph data. Convolutional neural networks can naturally operate on images, but have significant challenges in dealing with graph data. Graph images are a special case of graphs with nodes lie onto the lattices. Graph embedding tasks have a natural corresponding with image pixel-wise prediction tasks, such as segmentation. While encoder-decoder architectures like units have been successfully applied in many image pixel-wise prediction tasks, similar methods are lacking for graph data. This is due to the fact that pooling and upsampling operations are not natural in graph data. To address these challenges, we propose novel graph pooling and unpooling operations in this work. The G-pool layer adaptively selects some nodes to form a smaller graph based on their scalar projection values on a trainable projection vector. We further propose the G-unpool layer as the inverse operation of the G-pool layer. The G-unpool layer restores the graph into its original structure using the position information of nodes selected in the corresponding G-pool layer. Based on our proposed G-pool and G-unpool layers, we develop an encoder-decoder model on graph known as the graph units. So we have a graph convolutional networks, and now the graph pooling layer is. So suppose there are n nodes in the graph, and each of which contains C features. This graph can be represented by two matrices. Those are the adjacency matrix. A is the adjacency matrix, and the feature matrix X. So like any other, and the ID returned by the rank, because we are ranking, like it's a node scoring approach for pooling, for graph pooling. Once you get the nodes that you want to downsample, then you can do whatever you do for unit. Now we use it for graph unit. So by projection and getting the top k nodes, we are downsampling. This is how we go from higher adjacency matrix to lower adjacency matrix. So this is a kind of node scoring approach. We call it node scoring approach in hierarchical pooling. So we propose the layer-wise propagation rule of graph unpooling layer. You see an illustration of the proposed unpooling layer. First we do G-pool, so we have a quotient level, then we do graph convolution or any other thing, any other like graph attention, like graph isomorphism network. Then you do unpool to do upsampling. Instead of downsampling here, now we are upsampling to get the original. And now you get the reconstruction error here. So we first apply a graph embedding layer to convert nodes into low-dimensional representations. Since original inputs of some datasets like Cora usually have very high dimensional feature vectors. I think for Cora was 1,300 something. So it's huge. So first you need to reduce it. Then you do whatever I said about downsampling of the graph, coarsening, and then upsampling to get the original graph. So this error is the reconstruction error. So we do it for Cora dataset, CiteZero dataset, PubMed dataset, Colab, Proteins, DND. So it's even better than diffpool by just 1%. By just 1% better than diffpool. But diffpool is better than GUnit, you see. So sometimes diffpool is better.